perceptron. I will go into the detail further as an example. To solve a non-linearly separable problem such as the XOR operation. So in the XOR operation, we know, for example, we have or given x1 and x2, 0, 1 and 0, 2. We know that the pattern space can be defined in this way. This is your pattern space. At point 0, 0, then you have 1. So here it is 0, here it is 0, this point it is 1, and at this point it is 1. What I destroy, that is represented over here. So at this point is 0, it is 0 over here, it is 1 here and 1 here. This is your x1 and this is your x2. So when x1 and x2 are 0, 0, the value is 0, like over here. And if your value is 1 and 0, okay, so your x2 is 1 and x1 is 0. So this point again is a 0. So this problem cannot be solved, as we can see, using one single line or one hyperplane that we call. This problem cannot be solved like this. How can we solve this problem? Now this looks like a separation of the red and blue dots. So for that we need to define a hyperplane that separates the two kind of classes, the red and the blue. So we need two lines here. So for this we call the convex regions, open or closed we can say. So these are the convex regions we have to define to solve this kind of problem. For this we would at least need two neurons, and they will be structured like this. Now let's see how we can solve this. Okay, so if we set the first part is designed like an AND function. Next is designed like an OR function. So for 0, 0 we will get 0. You can see the AND function. So only this value will give us 1. And we set the weight values accordingly. So we have to set the weight values such that only when the value of x1 and x2 are both 1, we get a 1 from the classifier. And for the OR operation, we get 1 when either of the values are 1. For this, we need to define the weight values accordingly. So the classifier can give us this kind of output. What we are trying to do is design an XOR operation. And then in the next step, it will be the combination or it will take the input from both of these design functions. So for y1, when it is 0, 0, you should have a 0. And in both cases, we have 0, 0, 1, 0, 1. So it should give us a 1. Otherwise, when both are 1, it should give us a 0. So we define the weight values accordingly, set the weight values for our neuron, multilayer perceptron. These weight values I'm talking about. We have to set the values such that the output is that of a XOR. So the MLP will work as an XOR function. So we started from here, and this should be our output. So only when the values are dissimilar should we get a Y1 and Y2 combination. When they are 0, 0, the output should be 0. And then when it is only this value will give us 1. And these correspond to this region. So we have converted our AND used one neuron will be designed to perform this, the other will perform this, and the output of both of them will be input into another one to give us this final XOR operation. So we can define or design our problem like this. One of them will define this boundary, the other neuron will define this boundary. So and the combination of both of them will define some kind of like AND operation, and both of them, the combination of them would give us the XOR result. So any input we give here as x1, x2, the result will be your XOR operation. So what we have done is we've tried to solve a problem that is not just linearly separable. We used the existing functions that we had. So we designed our OR function like this linear boundary, and the AND operation like this. So exactly what we have done here in the XOR operation, so a combination of AND and OR we have used. So this one will perform one function, this one will perform another function for the input, and then a combination of them will be applied on this function to get us the required output. So we used AND and OR operation and a combination of them to give our XOR output for any given x1 and x2. So we already know how we define a data set. It is composed of your input x1, x11, x12 up to x1m, and you have where these are your predictor variables, or now we can call them features, and this is your output or your target. This will be your target, and these x's are your input. So we have to first determine the structure of the neural networks, how many nodes will be there, and what will be the weight of the links. Here now we have what we have studied so far. We have used fixed weights because we already know what we are trying to get, and it is easier to find the weight values mathematically in the examples that we have discussed so far. But for a larger network, when we have a very large number of inputs and large number of weights, for example, if we have 100 neurons in the input layer and 50 neurons at your hidden layer, so imagine for a fully connected network, what will be the number of weights that we have here? What will be the weight matrix that we have here, size of this weight matrix that connects the input layer to your hidden layer? So this is your input layer, this is your hidden layer. We need to define all the weights here. So for determining that mathematically will be nearly impossible. So we have to find and make the algorithm learn these weights on its own. That is machine learning. So what about how many weights we require? Okay, if we have at one time we give features from x1 to xm as the input, and we have k number of nodes in the hidden layer. So how many weights we require? So m plus 1, this input w0, and then multiplied by your k number of hidden, because it is fully connected. So multiplied by k number of hidden nodes, and then for the y we will have at least, if only we have one node, we will require k plus 1 weight values. So these are the number of weights for a simple neuron, one output neural network, multi-layer perceptron. So how can we now define the error function and find the weights that minimize the error? We have already defined an error function earlier. Wx minus yi. So we use this function. For simplicity here we define n wx. Just simply replace your f with this. And we call this the output of the neural network. N will be your output and y is your target. So y is what we want to achieve and n will be your output of the network. And what we will try to do is minimize the squared error. That is the basic idea. So if we have an input for data sample 1, x11, x12 up to x1d, d is the number of features and n is the number of samples. So the output and y, and we define t as a target. So now y is replaced with t, that is your target, x is your input, and O is the actual output of your network. So we can rewrite this error function. T is the target and O is the actual output. This is what we want to achieve, the target, and output, actual output is what we obtain from your neural network. And this can be solved. We have to update the weights so that our weights can be learned to give the required output. So we have to update the weights, and that can be done by error backpropagation. So partial of your error function with respect to the weight values is basically the sum of the previous values that are coming, all the error functions up to 1 to n, where n is the number of samples, because error is basically summation of all the errors from 1 to n data samples, and we need to evaluate for each w the partial of our error en. So all the weight values we have to update, and for that we need the partial of the error function. Only if we take the partial can we update the weights using back propagation. So we have defined the error function for given input data sample and your output. We can write the first output as ON1 and some output ONK, and total number of outputs are M, so we can write the last one as ONM. And we define the weights that exist between this node K and this node J as WKJ. And the output of this node J at the hidden layer is HNJ. Because this is J and N is the node from where the input is coming, so all of the neurons, so all input will be utilized to calculate the value of H and J, and the weight values between the input layer and the hidden layer will be defined by this is J and I. So I is the input and jth neuron. So the weight value between ith input and jth neuron is Wi, and the weight value between hidden node J and output node K is defined by WKJ. This is how we read. And before we used Y, now we are going to replace it with O as the output. So for this specific O and K, it takes the input from the previous values that are coming from our neural network. In order to update the value or obtain the value of O and K, it is basically because this is fully connected network. So first will be W, K, O, K naught, and then we have W, K, J and H of NJ. So this value multiplied by this value, and from value J value from 1 to P. Why 1 to P? Because there are P hidden nodes in our previous hidden layer. So for calculating this O and K, all these 1 to P hidden nodes and multiplied by their weight values plus one additional value that will come from here, WKO, and then we take the exponent using the f function that we defined earlier. And how do we define the hidden values? That will be okay, so all the values that are coming from the previous layer, n1 to nd, right? So xn to I, where I is from 1 to d, all these values multiplied by their weights. And how we have defined the weights? With ji. So only for this node j, it will be xn1 multiplied by this weight, xni multiplied by wji, and then xnd multiplied by this weight value at this node. This will lead to only one value, and this ONK is not only dependent on this, it is also dependent on this. right? Similarly, it is also dependent on all the other nodes and their estimations. So now for now, we are just tracing and setting up or understanding for back propagation. ONK will have the values, all the weight values multiplied by the H values. Then H and J will be first summation and then classifier of all the values that are coming into this node J, jth node. All the values that are coming for the jth node multiplied by the weight values, sum them up, and Wi naught, it will be coming from here, first weight value, and then your error function will be defined by T, which is the target, and O, which is the actual output. This is how we will define our error function, and if we can write it openly, then T and K is our target. This value defines the input because it has the X value. And we know your H of Nj is defined like this. So this is H of Nj multiplied by Wkj. Wkj multiplied by the value that is coming into your H of Nj. That is from first layer X and I. So we repeat this. O and K is taking values at node K at the output, which is receiving values from your node J, the hidden layer, which is again taking values from the input layer of x1 to xt. So now we can calculate error function with respect to weight Wji and then Wkj. So if we want to estimate the error over here, at this point, we have two weights matrices. First is from input to hidden, then from your hidden layer to output layer. And when we go from back propagation to update, first we go here and then we can go here to update all the weight values in our network. So all of these weight values, these links have weights. We have to update these weights, all of the network weights. That's the target. And for that, we need to take the partial of our error function with respect to the weight value at that specific link. But we can see taking the derivative of this final function, it is very complex. This part